Hi guys, welcome to my channel. And this is Rahul here, and today we're going to be studying about line integrals and its applications and its properties as well. Let me first tell you, or let me in this video we will also see what is the geometric meaning of line integral and where do we apply them. So first let us see why is line integrals so interesting. So for example, say we have a domain, say a closed domain, and then we have, say, a vector field in this domain. At each and every point we know what is the vector field. So since it's a vector field, let's draw arrows. So which means that at each and every point in this domain there is a function which is changing depending which changes in direction as well as the magnitude. So it's a vector point function, and the function changes at each and every point in this domain. So in case there's say this vector function is a velocity, and there's a vehicle which travels along a particular path. Let's take this path here just for an example. So the vehicle, let me put it in another color, maybe it's so a car has taken this path, and by taking this path, the car assume or gets the velocity of that particular function by traveling along this path. If it takes a different path, it assumes a different function. That is, it takes a different velocity field. So now the question is, say if you want to calculate what is the work done by traveling along this path, what would you do? You would take that function and multiply it by the displacement, right? But if it is a straight line or something, we could just do it easily, but here we find some kind of a complicated curve which is arbitrary, so we need to integrate along this curve, and here's where exactly line integrals are helpful in doing that. So this is what we're going to see today. So let us first take an arbitrary curve. Let us call this point M, and let's call this point En, and let's take an intermediate point EMI, ENI. So in terms of abscisses and ordinates, let's call this XI, YI, and this would be, let's say this change is delta XI, so this point here would be XI plus delta XI, and this point here similarly would be YI plus delta YI. And let's say the vector function is f, and this function f obviously is dependent on the path it is taking. So f is a function of, let's say, the p, where p is the points on this path, So P is a function of x comma y. So f is a function of the points along this path, and that's why it's a vector point function. So now we want to evaluate what is the, say let's assume f is a force. So let us evaluate what is the work done by moving along this path by using line integral. So we have a vector point function. We can write this in terms of components. Where I is the ith component or the ith vector, that is the projection of this component along the x-axis, and similarly for the y-axis, which will be j vector, or the jth, it's the unit vector. And similarly, we forgot something here. So let us assume, let us approximate this arc here with a straight line. I'm sorry, it's not a straight line. Delta Si. So if we do that, then delta Si can also be written as components, which will be delta Xi I vector plus delta Yi j vector. So this I here is just the ith point along the curve, and this I vector and j vector are the unit vectors along the direction of the axis. Since we have I here, just to denote that we have taken some points, some random points between m and n. So now the idea is what to say, what would happen if delta Si becomes very small. So as you can see from this picture, if delta Si becomes smaller, it means we are approximating the curve much better. So the smaller the delta Si, the better the approximation. So if delta Si becomes smaller, then this line here, say until this point here, would be more or less of a straight line, right? And if it becomes much smaller, much smaller, much smaller, say it reduces or tends to 0, which never reaches 0 but tends to 0. This is a very intricate concept of limit in mathematics. So as it tends to 0, delta Si is actually equal to the point at this point, mi. So now we need to evaluate the work done. As I told you, the function we assumed here was some kind of force. So we wanted to calculate work done. So work done is force times the displacement delta Si, delta S. So in our case, we have several delta Si's to be added on, so to be summed up, so that we can approximate the entire curve. So if we do that, we have a delta Si, and which will give us, so it's just the dot product of these two quantities, and it should give us right. So now let us say this quantity is A, which is a scalar quantity. So the dot product of this is called A, and it's just the multiplication of these two things here. And as I said earlier, what happens if delta Si tends to 0? Limit delta Si is tending to 0. So obviously then we are approximating the curve much better, and we will need more number of delta SIs to approximate it. So in the limit, this whole this thing will reduce to an integral for the curve, and let's say the whole curve is called C. So delta xi and delta yi are reducing to dx and dy, the differential quantities in the limit. And this term here is what is called as line integration, and we could calculate um, for example, the work done of the four vector point function f over an arbitrary curve or some curve C. So this here is the line integral for the vector field. There are a lot of interesting things which we can notice from this line integral, and we can also study about the properties in the next slide.